Hello, Eric and Mikkel. My name is Madeleine Prior. I am the English content specialist at 3D Natives, as well as the moderator, and I'm one of the co-organizers for this event. I just wanted to encourage everyone to please ask questions in the Q&A. This will be a discussion as we have had with all the other panels, but we would love to have about 10 minutes at the end to answer any of questions you have yourself. So please don't be shy. I'll be keeping an eye on it. And do upvote any questions you definitely want answered. I'll probably choose them. So let's start with talking about our two panelists who are here today. So thank you, first of all, gentlemen, for joining us. It's a pleasure to have you. I will start actually with just a little introduction of Eric. Eric Wyscik is the co-founder and managing partner of AMPOWER, one of the leading consultancies for industrial additive manufacturing, based in Germany. Since 2008, he has actually been successfully supporting OEMs from the aerospace, medical, and automotive sectors to identify AM applications and implement production capacities in their regulated environments. Recently, he was also involved in the production of a study on the sustainability of additive manufacturing, which of course makes him a great addition to our panel today. And now also I would like to introduce you to Mikkel. Mikkel Pedersen is the head of R&D at Oerlikon AM and leads a team of scientists and engineers to provide development support to the Oerlikon AM production sites and conduct research for the additive manufacturing industry. In this discussion, he has some particular expertise because he, apart from working in additive manufacturing since about 2013, he has been focusing on projects in aerospace, defense, and space. Previously, he worked as a design and analyst engineer for additive manufacturing for GKN Aerospace Services in the UK. His experience is actually mainly around metal AM, including EBM and laser powder bed machines, and ranges from design through materials and processes. His work includes flying parts, where the qualifications of AM material and novel design are some of the main challenges. I am so excited to welcome both of you today. It's going to be such a great discussion.
Thank you very much for the introduction.
Yeah, thank you for having us.
And now, well, let's get into the topic itself. So I actually wanted to start quickly with what we could consider a definition of sustainability. You might not know, but it's actually quite difficult to find a definition on sustainability. People don't really agree. The one that I think resonates with people the most, and which I think will help us define the scope of our conversation, is actually from the UN World Commission on Environment and Development, which simply states, sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Straightforward. So I think usually when we think of this, though, we think about it in terms of ecological needs. Of course, we've all heard about climate change and the issues, and we're trying to. And of course, AM is one of the leading technologies that has been put forth as a potential solution, thanks to its ability to limit waste, among other topics. But one thing that I want to make sure we also will focus on a little bit today is that sustainability is not just about the environment, it's also about humanity and health. So we will not touch on it a lot, we'll mostly be talking about environmental concerns, and I think because of the expertise of our experts, we'll probably also be focusing mostly on metal. But just something to keep in mind that sustainability is a much wider topic than you might originally think. And well, I think we can start with just a general question to lead the discussion, which is maybe a broad one, but AM is supposed to be sustainable compared to other technologies. How true would both of you say this is?
I would say it's very true. Compared to traditional manufacturing methods, we have a lot of opportunities with additive, whether it's all the way from designing parts that give better performance, lighter weight, or whether it's in the manufacturing chain of simplifying the whole process chain, reducing consumption of materials and energy in the manufacturing. Of course, it's not a universal truth. You can also do, let's say, less sustainable ways of using additive, something we probably will talk about later today as well. But for me, yeah, AM is a sustainable manufacturing method compared to traditional.
Great.
Yeah, I think I completely agree. In general, it gives us all the tools to be more sustainable with the technology. As mentioned, reducing materials, reducing weights, optimizing parts. Of course, there's always exceptions. And what we also see is maybe because the AM technology is a younger technology and there's a lot of startup applications in the industry, maybe it's a little bit at the forefront and looking more on this topic of sustainability. But when we look at conventional technologies, if we improve those as well, they can catch up to AM, and so it will be a tighter race in the future with conventional technologies catching up, becoming more sustainable. But in general, I think AM is a very good start to reduce our footprint on the Earth.
Well, that's certainly a good starting point for our conversation. And actually, a slight follow-up, which actually is similar to something that's asked in the chat, which is, what would you say makes AM particularly sustainable for an industry like aerospace, particularly if you have any examples when you compare it to traditional methods?
Do you want to go first, Eric?
Should I start this time? Yeah, I mean, for the aerospace, when we look at you introduced that sustainability is a very complex topic with many aspects going into the overall sustainability of the product. So I will just break it down to like two components that are probably most likely everybody's familiar with. One is the production process of the part, which can reduce emissions, waste, and so on. And the other one is then the actual lifetime of the part with a more efficient turbine component using less fuel, a lighter part, making the whole product lighter, or a more efficient hydraulic component, reducing the whole complexity of the system. So, and additive manufacturing has the advantage that it plays to both of these sectors. On the one hand, in the manufacturing process, due to this near net shape manufacturing capabilities, we need much less material going into the process. And with many materials, especially with titanium alloys often used in the aerospace industry, most of the energy that is actually in the part is already in the raw material itself, because it needs so much energy to create the raw titanium ingots. So here, if I reduce my material use already in the production significantly, my footprint of the final part is reduced greatly. And then utilizing the design freedom, optimizing my weight, optimizing efficiency of the product itself, that of course has an additional big effect to then create this large opportunity in the aviation area to create more sustainable products using additive manufacturing.
Yeah, and I think to build on this, I completely agree. But also looking at additive in a greater environment and ecosystem, not just as a single technology. Hybrid manufacturing, joining multiple manufacturing methods to make the most out of our materials to be optimized. Not spending at the additive process to making simple shapes, but maybe using a traditional manufacturing method, shaping materials in forming or machining or casting or forging, and then adding extra features on it with an additive process to reduce the overall shape that has to be done in the billet shape, and thereby we save material. So it's important not to look at it only on its own. Maybe one thing to add to Eric is also in the maintenance, repair and overhaul, the MRO section of additive. Again, life extension, repair of the components to avoid making a new part every time, but we can repair, bring the life back into our components, and therefore save on the energy to produce the parts and maybe also materials.
That is a good point, and one that we don't often discuss, that with additive, well, it's faster to make these spare parts and also able to, well, especially with DED, repair parts that have already been made, which certainly cuts costs. But I was wondering, because you both mentioned titanium, and I know that often, especially with titanium, they work with powder-based technologies. Would you say that there are some issues that are related to sustainability with these metal powders, and why? What are they? And if you have any insight, how can we overcome some of these barriers as well? That makes sense.
Well, titanium powders or titanium is an expensive material and a reactive material. So it means that when we process it in powder form, we have to be very careful with the atmosphere. So we use shield gases in the processing powder bed or in the DED process. We also do titanium with wire. It's wire-based titanium process as well that are used there. So it's not only on powder, but of course, creating titanium takes a lot of effort. A lot of raw material have to be mined to produce the material. So although we can say that it costs also a lot of energy to work with titanium, is also one of the areas where we have a big gain by reducing the amount of material we have to use in the manufacturing. In aerospace, typical titanium parts easily have a buy-to-fly ratio of 5:1. So we have a lot of opportunity to reduce this. There's even cases there where they're down to 1 or 1.1 buy-to-fly ratio. So it's very good material to reduce the effort on working on machining and processing, reducing the material consumption. So I would say titanium is perhaps one of those materials where we see a really good opportunity for additive to make more sustainable components.
Yeah, we're looking at it from a production side. Titanium is probably the most favorable material. Not only that we save a lot of energy, but also if we machine the material, it's a very hard material to machine. So even conventional processes need a lot of energy to produce a part. So here, additive technologies have a large advantage. You mentioned that with titanium, we are often looking at powder bed processes, although I think it was mentioned in the talks before as well, that the wire arc technologies, especially in aviation, are getting more and more popular, and many of those components, not even like new designs, but just one-to-one replacements of large milled parts are created with wire technologies. Here again, we see the big advantage mentioned by Mikkel, that we have a buy-to-fly ratio of those DED parts of maybe like 2:1, maybe 3:1, compared to 5 or 6 or 7:1, compared to the forged or plate material.
Okay, so yeah, that absolutely makes sense, and it's true that I always forget about wire arc, but it's true that it's becoming much more used, especially in the aerospace sector. And I can see certainly the advantages of having AM over traditional methods, especially with something like titanium. But I would ask, when it comes to parts, especially one of the concerns people have with sustainability is that when you have something like qualification, you might need to make a lot more parts. Is something like that preventing AM from becoming even more sustainable if we have to make more parts just to make a qualified one? Or can you think of any ways that we might be able to overcome certain barriers that we're still seeing in the industry?
Qualification certainly is a big challenge in any material in additive, not just the titanium. I guess one of the specific challenges of titanium in additive is it's often used in more critical applications. So there we have the additional burden when it comes to the qualification. We have to be very sure of the material performance when we make applications that have an impact on the reliability of the vehicle that we're operating. And on top of this, with additive, we also have to consider the surface on the parts. So when we print a part, what surface condition do we have that can affect your fatigue life. And all of this becomes a very, very difficult thing to manage when creating material data. And this is then where we come to from the aspect of qualification. We're producing large quantities of coupons. Everybody we talk to, our customers and competitors, are producing volumes and volumes of fatigue coupons, tensile coupons, cubes for material analysis. And every time we make a small change in the process, if we change machine, if there's differences in the process chain, we have to go through all the loops of testing and qualifying the material every time. And this is one of the big barriers. And there was the talk earlier in the event here as well on the status of qualification. And it is really a challenge in the additive industry to get to a point where we have enough trust in the material that we can reduce the effort we put into qualification. And this, of course, creates a large amount of almost, you can say, waste, because we just print a coupon, we break it, and then look at the result, and then we are ready to throw the material away or recycle it in the ideal case. And this is a big burden, not only in the material used, in the energy used, going to, and everybody is doing it almost individually. There's not so much collaboration with it, and we have hundreds of parameters to play with in the additive processes typically, and small variations of this means that we have to test all the extremities, all the corners of our process map to make sure that the material we produce is fine. Solutions could be to go in the direction of simulation. What role could simulation have in replacing some of the testing? But I think that's a really big, interesting topic, and I want to let Eric comment his input as well on this topic.
Yeah, and of course I agree that the more additional test material, coupons, or test parts I have to print, this depending on then the serial number of serial parts, is additional material, then of course impacts the overall footprint of the production. Maybe a completely different look at it as well, when going away from just the qualification of AM, but looking at the high requirements in the aviation industry towards the raw materials. We also see that generally regarding what kind of material is required, that recycling rates within the raw material are much lower than maybe in other industries due to cleaning issues, purity issues, and especially, and that is not true for AM, but for all metal technologies. The more we are achieving a higher recycling rate in the raw material production, the more sustainable we can get our product. So here there's also a lot of potential by better cleaning technologies. There are some companies now looking at the powder production, focusing on only using recycled material, and then using special cleaning and quality assurance processes to then achieve this high material quality to meet those demands and requirements in the qualification of aviation as well.
Okay, so we actually touched on quite a few important topics, I think, with both of your answers concerning sustainability, and we'll get to all of them in the questions. And I'm keeping an eye on the Q&A. We already have some very pertinent ones. But I did just want to actually touch on what you were speaking, well, both of you spoke about a little, which is the importance of software in making AM more sustainable. You briefly talked about it, but how important would you say it is to have these softwares for simulation, for in-process monitoring, for topology optimization? What is the role they are playing in making AM more sustainable, especially in an industry where weight is very important and material is very important?
Yeah, I see the main benefit, maybe not in the manufacturing process itself. As Mikkel mentioned, of course, with improved optimization or quality assurance method, we can maybe reduce waste material in the process. But as you mentioned, I think the main advantage is in optimizing the part and then fully utilizing the freedom of design I have with additive manufacturing, and creating topology optimized, weight optimized parts, fluid dynamic optimized parts, to decrease or increase the efficiency in the lifetime of the part. And here, of course, depending on the industry, those efficiency increases can have a large effect. And there's other industries probably where this is much less true. For example, when we are looking at implants, which are often manufactured additively, here the savings of an additive implant compared to a conventional implant in the life cycle of the part itself is probably negligible. But in aviation, of course, if I save a kilogram in weight, my sustainability of the whole product will decrease significantly.
Yeah, I agree with Eric. The real benefit is on the upfront. It's designing parts. It's taking the components to the next level, really taking advantage of the additive technologies. And here we actually have some challenges. It's a paradigm shift from a design perspective. This is some of the areas I come from, right? I used to have a 3D program where I could make shapes that my machinist will come and punch me when I sent, can you machine this for me, or make it in casting. And now it's the opposite direction. I can almost imagine shapes that I want to make them apart, but my tools for design are not made in those kind of designs, so I cannot realize them. And until I can get that 3D shape, I cannot create the part that really of the optimization softwares, whether it's flow or strength optimization, to really go to the extremes that we potentially could get for AM. And the representation of the shapes. If we start to make parts with a lot of cooling channels, the small features, file sizes becomes very big. It's difficult to manage. So the whole data aspect of additive is a really, really interesting approach or topic, because it also in the supply chain becomes a challenge. If we have large volume lattice structures, is a classic type of structure to put in. And if it's generated from your traditional CAD software, the file sizes are so big that the printers in the current technology struggle to handle the file sizes and make these parts, and it becomes a very slow process. So going in the opposite direction of making something smart. So being able to create the shapes you want to do, being able to manage the data, making cooling channels in complex parts, taking advantage of structures, maybe even starting to make these parts that are built as one in additive. We've seen them relating to laminar flow wings. That's sort of an integrated part that you, with some actuators, can change the shape because the assembly is printed as a whole. So really, we see some opportunities that we go there, but we have to be able to create the shapes because it is a digital manufacturing process. And if I don't have a geometry, a shape that I can tell to my printer to make, I cannot make it. It's not just in the old days, made a paper drawing and the machinist knew that when there was a line of dots on the part, that was where he was going to drill his holes. We have to create those features in the CAD model for it to work with additive, and this is the challenge. Of course, also with the manufacturing, using simulation tools to understand the process parameter development, and understanding what influence can we do. We're seeing a trend towards people using multiple parameters to build a single part. So not this generalization that we have, here's my parameter for Ti64, any part of any shape I put in machine, I press the same button, is this the process parameters, but using different parameters for different parts or shapes, or even multiple parameters for a single part. And to really be able to do this, we have to use simulation to put in the scan strategies, the vectors, the laser power, whatever it is, we have to control in our process parameters. And this can also help us make the manufacturing more efficient. So, and therefore using less material, less waste, linking this to optimization analysis of distortions in the part to avoid that we have to throw our parts away afterwards, because the thermal management, titanium is a terrible material to print from a distortion point of view. So if you make it too thick, it will crack, and if it's too thin, it will distort. So understanding how we can find the sweet spot so that the parts are great is important. And then the further steps in bringing in information from the in-process monitoring. What can we learn about the manufacturing process that helps us to qualify the part instead of having to do additional NDT methods later in the process? Not wasting resources working on a part that is already bad. It's something we often see as an issue. We print a part, we think it's good. We do all the machining, the surface finishing, the coating, we do the final inspection, and then there's a small defect in the part, and we end up having to scrap it. And that's a lot of wasted resources and energy. Of course, also for us and the customer, it's time and money. But from a sustainability point of view, there's also benefits to have by understanding the process. And here, really, simulation and software is key parts for all the way along the manufacturing and design chain of these additive parts.
Indeed, and it's interesting because we often see AM as just automatically more sustainable technology, but that's not entirely the case. There are things that must be going into it, and clearly we still have a long way to go. Actually, that ties into a question I wanted to ask, which is pivoting a little bit. But we mentioned DFAM, especially, but what would you say were other potential barriers to making vis-a-vis AM and sustainability and making aerospace more sustainable with AM? Like, what are the issues that still need to be addressed within additive manufacturing and the production process to make it into an even better method?
Well, we need to open up for more parts to be made. So one option is cost reduction. Today, additive is still expensive. Everything you make in additive in aerospace is expensive, but additive is an additional level to this. So helping us reduce the cost. We talked about some of the things: simulation, reducing the NRCs, so testing cost, qualification cost, creating the materials, creating route for qualification, like the other panel was discussing about. Is a key aspect to make it easier, not easy, but easier, having some controlled processes that we can follow for qualification, and not everybody have to find their own route to how we qualify these material processes. We need to understand our process better. As a user, we know that there's instabilities in the process, and if we want to push the limits of where we put our components, want to go to higher quality or classification parts, more critical parts, then we have to be absolutely sure that the material we produce is as good as it has to be every time we make it. Or if it's not, that we are able to detect when it falls outside the quality requirements, either through in-process monitoring, subsequent inspection. And these are some of the big challenges I see, in addition to what we talk about with DFAM and the opportunities to create the shapes. And of course, having the people behind the computer screen who can understand the process and take advantage of the capability, which again leads back to the first problem. And as a stress engineer, and this is how I got in trouble with AM, I said, what is the mechanical performance so I can run my topology optimization? I went to our material scientist, can you just give me some numbers? I just need some Young's modulus, strength data. And the question was not so easy to answer, because the material changes with a lot of factors, and this is inherently an issue that sort of ties the whole thing together in a circle, that until we have a control on material, we can't really do the optimization on the parts, because we have to understand exactly what is the material performance. And then it goes back and then change that. When I change my design, maybe I get a different microstructure, then I get a different material performance, and then we're back down to the first point of how do I make my part for this component.
Maybe one addition, when we are talking of the powder processes itself, there's also a lot of development going on, and they have to be intensified on new powders bypassing the gas atomization process. So getting titanium powder directly out of the sponge, or increasing recycling rates, so that again the raw material already has a much lower energy footprint before going into the AM process. Of course, on the other hand, this additionally will take a lot more qualification efforts, again now going to other raw materials. But in the long run, those reduction of energy in the raw material will then give a much higher sustainability.
So as you could expect, some give and take no matter where you are. Well, that makes sense, and it's true that, well, testing and training are areas that we do increasingly need in AM. I just wanted to ask specifically about the recyclability of powder. It's something I know we touched upon with both of you in our discussions. I wanted to ask well, two questions actually. One, which is of course, how will improving the recyclability of powder help with sustainability? What is the impact it has on it right now? But also to you specifically, Mikkel, if you could talk about the health aspect of powders we discussed. There can be some controversy in terms of health, how we can make metal powders especially work to make them more sustainable and better when people are working with them. So I know that was two questions, but address them however you'd like.
Yeah, if we start with the health aspect, working with metal powders is still relatively new, at least in the way that we operate with it in the additive technologies. At least when you think about how close the operator gets to the powder. And this is a key aspect to ensure that the long-term effects of working with powder isn't going to harm our technicians and engineers in the process. And this is something that will be a key aspect from a sustainability point of view to bring forward into the manufacturing, to ensure that it's a safe operating environment, whether it's all encapsulated in the machines or whether it's in the PPE that we use for the operators when they work with the powder and are exposed to the powders. So this is a huge challenge. We don't know what is the current situation. We haven't begun to suspect or project what would it be for people who've been working with this without test PPE when they operate with the powders. I know from an Oerlikon point of view, we do health checks, blood samples to understand, do we have people that works with nickel alloys, do they have an increased amount of nickel in the bloodstream, etc., to make sure that the means we have in place to protect our employees is sufficient to avoid that we have similar to what is known in the coal mine industry with the iron lungs or the lungs full of powder. You could imagine if you work with powder over a long time, all the fines would go in there, and some of the materials are absolutely not something we are benefiting from having in our bodies. So really understanding how can we ensure that we're not making manufacturing more dangerous by going to additive manufacturing compared to the traditional manufacturing method is also an aspect that has to be looked at from when we look at the sustainability in AM.
Definitely. As I said, we always focus on the ecological aspect, and I think even with powders, that's something that needs to be considered. But health is certainly an area where it needs to be sustainable over a long time, especially if we're switching to AM on a more permanent basis for industrial applications. And then with powder, so one of the, just repeating my former question, because I think I gave you both at once, if you could both speak a little bit about the importance of increasing recyclability of the powder, where we are now and how that affects the sustainability, because it's true that we're increasingly seeing higher recyclability rates, but it is a consideration, especially in industries like aerospace, where you need qualified parts.
Yeah, so from a powder aspect and the actual consumption rate on the powder is often one of the areas where the sustainability impact of AM is exaggerated. People assume that we use all the powder over and over again, or look at it in a very limited volume, and this is an issue if we don't, because then suddenly our consumption rate becomes a big negative for the industry. In particular, when we look at some of the powder bed industries, a typical build solidifies between 5 and maybe at a max 25% of the volume of powder loaded into a machine. So potentially, if we load 100 kilos of powder into the machine, we take 95 kilos of powder out again. And if we don't use this powder, then our buy to fry ratio is terrible. It's not good at all. So we have to ensure that we can use this powder again. that we can test it, we can ensure, we can handle it in a way that it doesn't get contaminated, get mixed with all sorts of other things, not exposed to atmosphere with some of the reactive materials where we get oxygen and moisture pickup on there. So the whole handling aspects becomes a major portion of ensuring that we have a sustainable technology. And this is where we've done some tests on how we can recover and reuse the powder. There's a lot of industries right now starting to go into AM that will use a cycle counting approach to say you can use your powder in 10 cycles and then it's no longer trusted or good. And when we look at this, we see this as a very wasteful method. And a small example that we made with a space part, not an aerospace part, but a satellite part, was we need 200 kilos of powder to fill up the build to run the equipment, and we only consume about 20 kilos of powder. So to make this part, we of course have to fill up every time we have 200 kilos into the product or to the powder bed. And when we then run 10 builds, we have a leftover of 180 kilos of powder that have seen 10 cycles, and now we have to scrap it. And when you look at that compared to the initial amount of powder we put in, if we use that approach, we have a higher wastage of powder in the order of almost 50% than what we would like to think that we can do with additive. So we tend to use a different approach. We tend to control powder, test powder, and continue to monitor the health of the powder, and therefore not rely on a simple cycle count, but with test methodologies, ensuring that our powder stays within spec during the process. And with this, we can get to a much higher consumption rate, and we don't have to have this leftover powder that we have to scrap because it's seen the max number of cycles. And this is where we've seen some really differences in the sustainability aspect. Because if you only look at it from a single build perspective, then of course you're going to use the 180 kilos that come down. But when you scale this up and you have 10, 15, 20 machines doing this, the volumes of powder we're operating becomes really, really difficult if we're left over with this. The biggest machine we have, which we operate with Inconel, we load almost 900 kilos of powder in for a full build. And again, we solidify, I think, 50, 60 kilos of that. So we can see the volumes, if we cannot have a really good, robust methodology for reusing, recovering, testing the powders and maintaining the quality of the powders, becomes really unsustainable because we have to scrap a lot of powder.
Yeah, I can only second that. In the study we have done, where we modeled the processes, we've seen across all of the alloy groups that the recycling factor is one of the most impactful factors on the overall CO2 footprint of the part. So if we can't recycle our powder efficiently, AM technologies will in the end have a worse footprint than conventional technologies.
Which is certainly a consideration. Well, we're going to get to the Q&A section, so I do just want to ask one last of my own questions on something that I think is important, which is post-processing. So post-processing is also a key in AM, with AM technologies, especially when you're working with metal. What would you say are some of the sustainability issues related to popular post-processing for the materials you're using for something like aerospace?
Yeah. Here, in my opinion, of course, it strongly depends on the process we are looking at. Some processes, when we are, again, considering, for example, milling as a post-process for finishing the part, then it's, again, mainly the energy we needed for milling the titanium or Inconel, which is also difficult to mill. But many of the popular processes for especially those complex AM geometries are like electrochemical polishing technologies, and there then we are again more looking at hazardous materials. What do we do with the chemicals? What we do with the very fine powder particles in the chemicals? Can we discard of those? Can we recycle those? Here it's then a problem of these waste materials. We need to find solutions for.
Yeah, I can only second that. It's a challenge. We use corrosion-resistant materials, and as an effect of this, we have to use some very dangerous chemicals to corrode those materials if we want to use these electrochemical and other processes. But at the same time, we need to have processes that allows us to maintain design freedom. If we go back, then all parts have to be CNC milled on all surfaces. Well, then we're back to the design freedom of a CNC machine. We don't get the benefit of AM. The other opportunities, we always look at post-processing as a way to remove material from the surface. What about adding? What about adding material to the surface? Other additive technologies, coatings, etc. What can we use in this direction to achieve what we're doing? Or can we use coatings and other additives to avoid machining? What if the tolerances of what I produce at AM is okay if I have a more flexible coating or sealing solution than your traditional sealment that we're doing? So opportunities in adding on top of your 3D printed parts instead of removing is another aspect where you can go in and address the sustainability topic.
Great. Well, thank you so much. As I mentioned, we have some really great questions in the Q&A, so I'm just going to turn to that for the last 8 minutes or so. The most popular question so far is actually, how about the energy consumption to produce the feedstock powder for AM with sustainability?
Maybe I start again. Yeah, here again, it strongly depends actually on the technology we compare the process to and the alloy we are talking about. Again, when we look at the titanium alloy, the additional energy we need for creating the powder is compared to the overall energy needed to create the alloy very small. So this additional energy only has a very small impact. With aluminum alloy, this looks a little bit different. So here, an efficient powder production process is actually needed, or more efficient, to reduce the overall impact. So it's not an easy question to answer.
Yeah, but and I agree. If we can avoid some of the atomization processes, skip some steps to get the powder closer to the raw material. You know, making powder, you usually have many stages to transform it into different media. In some of them, it goes all the way to wire before you then make it into powder. So there's a lot of steps going into it, a lot of heat energy put into it. The other aspect is utilization. We always like to think that when we atomize powder, we just take all of it and use it, but we only use a small cut for maybe the AM processes. So the utilization of a larger part of the PSD that is created in the atomization process. So this is also where the interesting play between the different technologies. You might have some MIM materials that use some finer powders, your powder bed fusion that use the mid-range, and maybe your DED process then uses the larger particles in their technologies and processes. And by doing so, by using a larger portion of the powder that is produced in the atomization run, we also create a better sustainability. And of course, the opportunity to take the particles that are too big or too small for our use, remelting them, and go back into the atomization process. So it's not wasted material, but it keeps in the circle. So this is a big topic, and a lot of the wins in this is understanding the way that we can really use all the powder that comes out of this atomization process, because the range is big, and we always have some controlled ranges that we like to use. And what do we do with the rest?
Indeed. Well, thank you. And then we have, from an anonymous user, we have another question, which is going in a different direction, but quite pertinent. When we talk about sustainability, where would you say is the main focus? Reducing material usage or using more sustainable materials?
I think it's important to do both. I think we have to and we have opportunities to change and make new materials for AM. And when we do so, we should focus on not using rare earth materials, the materials that are expensive to extract, to the extent that we can. But it has to be a trade-off. Some of the good mechanical performances or heat performance comes from certain materials, and to push the limit of the material performance that would allow us to have, let's say, a more efficient running engine, we have to use certain materials, and maybe they are not so nice to extract or very energy efficient to extract from the raw material. So we have to look at both, and we have to be vigilant of this, and we have to look at the full chain when we make the decision of what materials we're going to use in the process. But if we use less material, it's a double win. You also have to extract less of these rare earth materials, etc., from the mining industry, and of course, avoiding to use materials where the mining what would you say, the miners are under high stress or in terrible regions like we see right now with a lot of the cobalt is for unsustainable mining areas. So avoiding to use this in our alloys. So, there's a huge aspect of this to be considered in AM, and there's a huge, as I said, development of materials and a lot of potential in this, and we should of course have that in mind when we select what elements we use in our alloys.
Yeah, I second that, and I wanted to add, I think we have to focus on both, because most of us, we are just starting to understand the whole process chain and what are the impacts on the overall sustainability. So we have to focus on both, and then see in the end, okay, for which application, which is the better route to go. And I think most of us are not there yet to identify which is the better solution.
Great. And well, we're running out of time, so I think this might be our last question. It just quickly gained in popularity. Specifically for Mikkel, could you comment on what methods of characterization or testing you use to evaluate the powder to know when to discard it? Of course, Eric, if you have insights in this, feel free to answer as well.
Sorry, I had a glitch on what was the last part of the question?
Could you comment on what methods of characterization testing you use to evaluate the powder to know when to discard it?
So this is very dependent on the powder. If it's reactive powders, titanium powder we talked about, oxygen content will typically be the cutoff factor, depending on the grades of titanium that you're expected to achieve. And we have to be vigilant and look at the bulk material. If we take a grade 5, it's about 0.2% oxygen. That is the limit in the bulk material. So this is what our customer expects is the maximum limit of the component. We know in the AM process we are not completely without oxygen. There will almost always be a small oxygen pickup. So our powder spec, of course, have to reflect this. So we cannot go to the same level of oxygen in the powder as we expect to get for the final component if we expect a pickup of oxygen in the process. And for every single material, we have to look at it. Are they going to pick up things? Reactive materials could pick up oxygen, hydrogen, whether it's from the atmosphere, moisture. Are we having a loss of elements, volatile elements that evaporate during the processing, being near parts? In particular, for something like an EBM process where everything is very hot, some of the volatile elements might evaporate over time. So it's not a one thing that you have to check on the materials. It depends on the materials, and of course, there's the chemical. Then there's also the physical characteristic of the parts. Loss of particles. If you get a shift of new PSD, then you don't get the packing density. Then you don't get your dense parts that you want to have. So there's a lot of things that we have to keep an eye on. But by understanding the materials, understanding the processes, we don't have to test everything every single time. We can build statistics to say these things change in this material. Certain elements in titanium, it's perhaps at least in laser powder bed, unlikely that you're going to have a loss or a gain of vanadium. So I don't need to check my vanadium content on my Ti-64. So by building up your knowledge and confidence of what change in your materials, you can then tailor the test approach to say, I only need to check these few items because this is what might change. And at a certain point, this will cause me a problem achieving what I promised the customer.
Well, I think that's time, but thank you very much, both Eric and Mikkel. We still have quite a lot of questions, so if you both stick around for the networking session, that'll be now. I highly encourage people to go and ask questions. I'm sure both would be happy to answer. Thank you very much to both of you for being here today. It was a fantastic discussion,